Okay, hello guys. Today we will be doing the first lecture of biophysics, that is electromagnetic waves. So I'm in between lectures right now, and this lecture is so small that I'll just do it beforehand. And it's very simple. The first 18 slides are just waste. As you can see, it's just explaining how many people failed and passed last year. Okay, very good information. Then moving on. The thing starts from here. Electromagnetic waves to a nature of light matter waves. Now, why is electromagnetic radiation excellent? Light is the most common type of radiation besides physiological maximum. This is very like surface level knowledge. It says that you need electromagnetic waves to see shit. That's so obvious. Optical methods, therapeutic application, yes, blue light therapy. You see all these you see on Amazon. There's like some red light face masks coming up. All these things are important, like therapeutic applications, optical methods. Of course, you can't see anything if they don't reflect back electromagnetic waves. You can't see anything. Your eyes won't perceive anything, and vision, of course. Previous knowledge, high school, okay, whatever. Leave this. Nature of light. Now, in chemistry as well, in the med chem lectures, if you watch them, you'll know that we have done even nature of light. We know that in some situations it acts like particles, in some situations it acts like waves. Okay? Velocity of vacuum and light, this is okay. Electromagnetic wave, interference phenomena. I'm going to explain interference because it's important. It's in the minutes. Beginning of 20th century, E is equal to HF. Okay, this is given by Planck. Okay, don't know its full name. It's given by Planck. E is equal to HF. We have done this in the first lecture as well. First lecture of MedChem, atomic structure. We did this. We did E is equal to HF, and we solved some problems with it as well. If you want to know what this is exactly and solve some problems, go back to that video, and I have timestamp so you can go through it. Now, interference as a wave property. Let's talk about the double slit experiment. The double slit experiment is one of the most craziest experiments in the whole of quantum physics. Quantum physics, not just physics. I'll explain to you. Now, normally, if we were to shine one source of light, okay, through two slits, okay, we would think if light was a particle, which Einstein and Planck had said that yes, they are particles. If they were, then particles would either go through one slit, go to either one of the slits, and fall over here or here, right? Like particles are going everywhere. They're going here, 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 everywhere. But if they're not gonna go through the slit, they're just gonna bounce back or something. Okay. But if they're a photon, these things are called photons, which are the smallest particles, no, smallest amounts of energy. They're called photons. The fundamental unit of energy is a photon. The smallest amount of energy that can exist in this universe is a photon. So that's what it's trying to say. If the photon was to pass through one of these slits, it would just go through and hit over here, and that's what you would see. But that's not what we see. When we pass light through it, this is what we see. We see a series of bright bands and dark bands. Okay, so what happens here? Why does this happen? So I want to explain this using a YouTube video. Let me just pull that up really quick. Double slit experiment. You guys should see this guy, Veritasium.
Fedezd fel a korlátlan ingyenes szállítást a Foodóra Próval, és regisztrálj most a kedvezményekért, mert jól esik!
Okay, I'm just gonna pause this and go straight to the part where he's explaining the waves. And here we go. This is how light behaves, okay? This is exactly how light also
wave
behaves.
fronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern.
You can see over here, I wish I could use
this pattern is created by
take a pair. Done. Okay. So over here, you can see two waves coinciding with each other. You can see that this area here has a higher crest than these areas here. These are the basically the light, the dark bands, and these areas over here, this, 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 these are the bright bands. In these blue areas over here, these are the dark bands. You can see that, right? Let me erase all of this once again, so you can see that. Okay, can you see it? I hope you guys see it. I hope you guys understand what I'm trying to say over here. Just gonna go back now to that. And because of this, we see a series of light bands and dark bands. Okay, they look something like this. You see a bright band, and we don't see anything like this. We can see something like that. This is what we see. Very fascinating. Okay, and this was explained because of the wave nature. Like that's the only way we could explain. Now let's talk about this constructive interference and destructive interference. Okay, we'll just zoom in here and talk about that. Let's take two waves. Oh, whoa, that's too flat. What? One wave is like that, okay, and the other wave is, let's say, like that. Okay. Now, if you were to put these two in phase, and in phase is basically what I mean by in phase is that the crests and troughs they line up. Okay, by crests I mean these top ones, or you can say hills, and troughs I mean valleys for these things. If I were to line them up, let me erase this. Let me draw another wave like that. If I were to line it up, just like that, what ends up happening? And if I were to make these two waves coincide with each other, these two, the crest of this and crest of this wave, would coincide to form a bigger crest and a bigger valley. Okay, so they both are built up on each other. So that is what we call constructive interference when they build up on each other. Okay, now that is when they're in phase, and in phase I mean their crests line up, their troughs line up, etc. But what happens when they're not lined up? So we have a wave like that over here, and we have a wave like that over here. You can see the crest of this is lining up with the trough of this, and the trough of this lining up with the crest of this. Okay, so what ends up happening is that they either, if these two waves have the same wavelength, the same amplitude, amplitude being the distance, like that distance, if they were to have the same, everything the same, they will cancel out, resulting in no wave at all. Okay, but if, let's say, the amplitude the amplitude of this wave, you can see that the crests are still lining up with the trough is lining up. But the amplitude of this wave, let me take blue here, these waves over here, if we take the waves, the amplitude of this wave is less than the amplitude of this wave. Okay, so when you interact both of these together, they don't build up on each other because they're not coinciding. They destroy each other and end up making this huge wave smaller. So when you combine these two, you get something like, which is still bigger than this one now, but then it has destroyed this over the wave and made it smaller. So that's destructive interference. Okay, they interfere with each other. If they build up on each other, that's constructive. If they don't, that's destructive. That is constructive and destructive. It's important. Later on, after I finish the video, I'm gonna go through the minimals. I'm gonna explain the exact definitions, what word you should use, what not. For now, understand the concept of this. Okay. Now, I just want to give you a random, very cool fact that I thought was very cool. Okay. So, quantum physics is this branch of physics which is absolutely crazy, discussing dark matter and all of these experiments which cannot be explained, okay, with the existing sets of rules that we have in the universe. One of them comes from the double slit experiment. There was a experiment conducted in 2007 in Institute of Debrecen, which till now, by majority of the scientists in the world, is considered one of the most weirdest results of an experiment ever. So what happened was these experiments, the double slit experiment, has been done before. People know when you shine a light through two slits, we're going to get waves. Okay, and what happened is scientists discovered a way to isolate the smallest amount of energy in the universe, and that is a photon. So photons are basically particles, okay, but they're also waves. Okay, it's very weird. The way they are is basically a small wave, but it's a particle. Let me try to draw what a photon might look like. Maybe like that. And it's enclosed in like this particle type thing. And this is the best representation I can draw of a photon. It's not a particle, it's a wave, but it's a small wave. And it's the smallest wave that can possibly exist. And this is a photon. So basically all of these blue balls are these photons. Okay, they're the smallest amount of energy that can exist. Now, when we shine for photons through these double slits, we know what happens. We get this dark band, light band thing. But in 2007, what they did is scientists observed each and every single photon. So they accelerated the photons at the double slit, and they did it while observing the photon. Okay, so they would do it very slowly. They would say, okay, fine, one photon has passed through this slit, the other photon has passed through this slit, this slit. They will notice every single photon. Okay, and what would you think happened? Okay, we would expect, okay, the interference, the light bands and dark bands still happens. But the thing is, when the scientists observed the photons, this is exactly what happened. They saw just two bright bands. And right after this, they conducted the experiment again. But this time, everything was the same, but they did not observe the photons. And guess what happened? We got light bands and dark bands. And this is one of the most craziest and unexplainable events in quantum physics till date. We don't know how to explain. It's the thing is, what I find the coolest is how does a bloody photon know if you're watching or not? It's absolutely crazy for me to think about. This is absolutely not related to the syllabus, nothing related, but I feel like things like this make me more interested in physics, so why not tell you guys as well, yeah? So that's really cool, guys. That's so cool. If you observe it, Neil deGrasse Tyson, do you know that guy? You probably know, you've seen his TikToks and stuff. He made a video on this. You should see that video. I'll link it in the media description. Watch that video. Blows your mind completely. Unexplained till now. So there's no explanation. If you can't live with that, then don't watch that video. Okay, moving on. The photoelectric effect. Okay, what is the photoelectric effect? Now, we know Young had conducted an experiment, that is the double slit experiment, to explain the wave nature of light. Yeah, the wave nature of light. But then Einstein also did his own experiment to show that light was a particle type uh, substance. Particle type substance, okay? What was this? So what he did was there's a few ways you can conduct this experiment. Okay? So see, let's understand the construction over here. We have a glass certain like tube. Over here at the entrance we have a small entrance like that. Okay? And at this entrance, we are to keep a quartz crystal. Over here, they've not mentioned it, but I know I'm just going to teach you a quartz crystal. Why? Because when sunlight is shined at a quartz crystal, only UV radiations get to pass through. Okay, and why only UV? I'll explain that right now. Now, we take a plate here. Okay, it can be any plate. Uh, it can probably made of, over here it says it's made of potassium. I've seen experiments where they use zinc plates, copper plates, whatever, it works. Okay. Now you take a potassium plate, fine, and what you do is that you make it negatively, you make it positively charged, because you can see the positive end, the negative end. Okay, you make it positively charged. Why? Now let's see what happens when we shine light through it. Now, we shine red light through it. Somehow we isolate that, okay? If we use a quartz crystal, usually we get only UV rays, but let's say we shine only red light on it. We shine red light on it, nothing happens. Nothing really happens. This is actually a circuit, okay? And over here we have an ammeter. Ammeter measures current, okay? So this is the experiment setup here. I think I should draw a separate thing over here. So let me do that. Okay, I'm gonna now just use the precision laser, and I'm gonna create slit here. Boom, boom, boom. Okay, this side is connected with a circuit. It's plus minus. Let's draw a plate here. Okay, here. Now we shine red light through it. What happens? Nothing happens. Okay, over here the ammeter, okay, which measures the current. Nothing happens. Ammeter. That's the wrong spelling. Nothing happens. What are we expecting to happen here? What we expect to happen is that when we pass green light, suppose we pass green light. Now, green light has more frequency than red light. Okay, frequency is directly proportional to. If you guys watch the MetChem videos, then you'll know. Energy and frequency are directly proportional. Energy and wavelength are inversely proportional. Frequency and wavelength are also inversely proportional. What happens when you shine green light is we suddenly see this current now. Okay, and that's fascinating. Why is there current now? So it turns out what happens is when light with enough energy, okay, or enough frequency is hit on a plate of any metal, photons are ejected out of that metal. Can you believe that? Photons are ejected out of that. Okay? So basically, what happens is these photons get excited by this incoming radiation and they jump out of the metal. And when they jump out, some of the photons they interact with the negative electrode and produce electricity. Okay? Now, what happens when you do blue light? Does blue light have more frequency than red? Yes, it does. So with blue light as well, this happens again. This happens again. We see that there are photons jumping out like that and then interacting with the electrode and forming electricity. What does this prove? This proves that photons exist and photons are packets of energy. What does this prove for Einstein? What did Einstein get from this? He got a Nobel Award, Nobel Prize in physics, yeah. But then he also proved that light acts as a particle, right? And those particles, when they're excited enough, okay, within the correct amount of radiation, they jump out as photons, boom, 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 interact with electrodes, form electricity. That's exactly what we see over here. Okay, we see E is equal to HF, yeah, and frequency over here is given as speed of light divided by wavelength. Yes, we know that because we learned that C is equal to mu mu lambda. How do you write lambda? Forgot. Shit, I'm so sorry. I don't know how. Mu, but C is equal to mu lambda. Frequency C is equal to frequency lambda. Okay, okay, yeah. So C is equal to frequency by lambda. So F will be equal to C by lambda, and that's exactly what we do here. Okay, so that's that, and that is us basically understanding how light interacts as a particle. Okay, this formula not really important because it's not asked in the minimals. Our professor said that the equations which are included in the minimals, those are the only ones which are important. That's me explaining you the wave nature of matter. Basically, like I said, waves of matter, Young's double experiment explain the electromagnetic radiation as both wave and parallel, but they were de Broglie's wavelength. We did this in medchem as well, and this is how we explained electron. No, we didn't explain electron microscopy. It's here. But yeah, we did de Broglie's wavelength. Okay, and if you go to my previous videos, there's timestamps, and you can just click on that and see the de Broglie's wavelength. We're basically saying de Broglie hypothesized that every single thing on this planet has a wave function. Every single thing on this planet, you as well. I'm emitting waves right now. You know, not those crazy. You know, those girls are like, oh my god, you're emitting like energy. You have like big energy. It's not. No, that's bullshit. By waves, I mean like waves, actual waves. Everyone emits waves. Everything. This thing emits waves. Everything. And to find the wavelength of those waves, all we need to do is h by p. All we need to do. So I can find the wavelength that this is emitting right now. How? I find the wavelength h. We know h 6.63 in the 10 raised to minus 34. And then momentum is m into v, mass into velocity. Okay. What's the mass of the sun? It should be 250 ml. So let's say that's like 250 grams. 250 into velocity. I throw it at some velocity, whatever. 1 meter per second. Yeah, and then I find the wavelength that this is emitting. Simple. That's de Broglie's wavelength. And de Broglie's wavelength for an electron is very important when we come to electron microscopy, and I'll explain that later on when we reach that topic. Electromagnetic spectrum, many things we have already learned in medchem, so that's that. And thermal radiation, give me some more time, I'm gonna learn that right now. Okay, so let's look at the thermal radiation. The thermal radiation, SS is an important topic. It's not included in the minimals. We don't need to know the formulas. So I'm just going to explain the general concept of this, but not going to go in detail. So let's look at over here. The main concept is black bodies. Okay, black body is very important. This formula not important at all. To learn Kirchhoff's law statement of here, that's that. Object emits electromagnetic radiation. The spectrum depends on the temperature only, and is independent on the material of object. Okay. Now, M black. What are black bodies? Black bodies are theoretical objects. These are not real objects. They are theoretical objects which absorb all the radiation that's emitted onto them. Okay. So there's this new paint on TikTok called Vanta Black. Yeah. It's like basically when you cover this a sphere with that color black, it basically seems like it doesn't seem spherical. Have you seen that TikTok? I don't think you have. If you have, then you understand what I'm trying to say. So basically, a black body is a body which absorbs all of its radiation. Okay, and that's why it's black. Theoretically, if I were to paint if this were a black body, I couldn't really see the shape of it. It would just seem like I'm seeing into a black. I don't know what to say, but let me show you an example of a black body. No, sorry. Yes. If we look over here, nothing really. Yeah, you can see this. This is actually a sphere, but then you can't really see it because it's it's almost a black body. So you can't really understand and see what kind of shape is it because it absorbs everything. It doesn't emit anything, so your eyes can't perceive what it is. That's a black body. Why are black body radiations important? Over here, we had Stephen Boltzmann's law and Wien's law, which is highlighted in the understand why. Okay, let's look at this graph. Okay, you know when we heat up certain objects like metals, for example, you start heating them up. You heat them up and they slowly become red. From red, they become yellow. When you're heating them up, yellow, they keep heating, they keep getting hotter and hotter, and final point, they become white. Yeah, that's when you know shit's hot. Okay? So what do you mean? What am I trying to say with this? Okay, over here. It says that frequency and intensity. Okay, you can see over here, this is 1000 Kelvin. Okay, at 1000 Kelvin, which is definitely lower than 2000, at 1000 Kelvin, the frequency is right here. The highest peak that emits is here. Frequency is in what relation with wavelength? Can you please tell me? I've asked this like so many times. Frequency is inversely relational, proportional to wavelength. So this, even though over here it has a small wavelength, a small frequency, has a high wavelength. But at a higher temperature, you can see that the frequency peak shifts from here to a bit forward. So it has more frequency, which results in a lower wavelength. Okay, so but then you can see that the intensity is more. Let me explain this again. So what is Wien's law trying to say? It says that the wavelength, the maximum wavelength, the peak wavelength, but over here they've given frequency. I don't know why. All the videos and explanations that I've seen, they use the chart over here is a wavelength, but they've used frequency. I don't know why. They say that the frequency, the wavelength max into whatever the temperature is at that point is a constant, which is this 2.9, 10 raised to whatever. Understand? Let's take this for example. I don't think this is gonna when I hit. Do you think if I hit it, it's gonna turn red and white? I don't think. So there are only certain materials in this world which can emit that property. Okay, and those are objects which emit electromagnetic radiation whose spectrum depends on the temperature. Some objects, those are only some of the objects. Some of the objects, their spectrum depends on their temperature. This is not one of them. This is not one of them. You are not one of them. Okay? Let's say this was one of them. I start increasing the temperature. It starts glowing. Okay? It becomes red, white, whatever. I track that light. Okay? And then I increase, and then I track the wavelength of that light. What happens when I track the wavelength? I see that if I take the peak wavelength, okay, multiply it with the temperature at that time, I get the constant, this constant always, whatever it may be. Okay, so this is the same thing. So what I'm trying to say here is this wavelength into this is equal to 2.9 into 10 raised to minus 3, and this wavelength into this temperature is also 2.9 into 10 raised to minus 3. Isn't that cool? That is really cool. I find that cool. What does Boltzmann's law state? Okay, he just stated that the intensity, that is sigma, intensity being what? The area under the whole curve. Okay, the energy basically. Energy. Intensity is different than energy. Energy is the area under the whole. It's also it can be found using this formula, which is the M black. That is the what was that? I'm really sorry, guys. The intensity of the radiation. So basically, this value into the temperature at that point into is equal to the sigma. So what is sigma again? The energy, the area under the graph. Find the energy. You can just use the intensity value, that is M, temperature at that point, and then temperature cube, not cube, raised to 4 at that point. Learn these values, very important. This we can. It's not that important, guys. Just trying to explain. This is for a 5 also. So learn these, learn this, and when I'm gonna be explaining the minimals, that's when the most important stuff is gonna come over. This isn't that important. Heisenberg uncertainty principle. Okay. Heisenberg uncertainty principle says that you cannot track the position and the momentum of elementary particle at any point. You can only track one thing at a time. You cannot track both at once. Okay. So what is this? Delta px is less or no, is greater or equal to h. H is being the Planck's constant. Delta x is the change in position in the x-axis. In the x-axis. Let's why we're using x-axis, because we want to boil it down to make it easy. Understand? We could take any point in the universe, but if we take only the x-axis, it just makes it easy. The position in the x-axis, so it could be here, 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 and the momentum, the speed at which they are traveling. here the momentum, that is mass into velocity. If one of them increases, the other one decreases. But the thing that is you have to understand is the what's the multiple? The multiple of these two. The answer when you multiply these two has to be greater than h. It cannot be less. Cannot be less. This is, and how do I explain? It's like this is the rule of life. It cannot be less. Let me show you this video by Veritasium. Then really great guy, and then I think you'll understand that because he explains things so well by actually showing that stuff. Heisenberg certainty principle.
Ha Messi átjön megnézni az UEFA bajnokok ligáját, egy dologra figyelj.
Today, I'm doing an experiment that demonstrates Heisenberg's uncertainty principle. So here I have a green laser, and I'm firing it down towards the front of the room through a narrow slit. Now that slit can be adjusted, so it can be made narrower or wider. And the laser spot is projected onto a screen behind it. So what do you think is going to happen to this spot on the screen as I narrow the slit? Well, let's have a look. You see exactly what you'd expect. The spot gets narrower and narrower. The sides are getting cut off by the slit. Makes complete sense. And if you stop there, you would never realize that Heisenberg's uncertainty principle is at work. But if you keep going, something strange happens. As you make the slit even narrower, the spot starts to spread out. Isn't that incredible? You're making the slit narrower, and yet the spot on the wall is getting wider. The narrower you make it, the wider that spot on the wall becomes. To understand this, we have to look at Heisenberg's uncertainty principle. Heisenberg's uncertainty principle is normally written as delta x delta p is greater than or equal to h on 4 pi. So what does this mean? Well, it's about the position and the momentum of a particle. So x is the position of the particle and p is its momentum. So delta x is the uncertainty in position and delta p is the...
Okay, few questions I know you probably already have is why we don't use h divided by 4 pi. I don't know honestly. These are not even included in the minimals, so I don't know why they're using only h over here. Now, why do you think the laser spread out when the slit got narrower and narrower? Because see, when the slit got narrower and narrower, okay, at certain point we saw that the circle was getting cut and cut and cut and cut, and then at one point it started spreading. Why? Because at that one point, when the slits get narrower and narrower, we can say, for example, when the slit gets narrower, we can tell with certainty that okay, since the slit is so narrow, okay, the photon is going to pass through this, and it's only going to land at one place on the screen. Okay, that is giving us what? That is giving us the position. Okay, since when the slit is wider, we can't exactly say on what part of the screen is going to land. It can be a wide area. It will be proportional to the distance between the slit, right? But when you make the area very small and we keep a screen right in front of it, then we can be very certain that the photon is going to pass through this narrow slit and then meet somewhere over here because it can't really go there or there, can it? That's what we can say. But then, as I said, this is a law of the universe. If we can calculate the position accurately, something with the momentum has to get messed up. So now what starts happening is it sees, okay, the place is getting narrower and narrower. That means the position is getting more accurate. And at the one point, it's like, okay, fine. If we take this, if we take the value of delta x and multiply with this, turns out it's going to be smaller than h. Okay, we're not doing this. This is the universe doing that. Okay, you see that? Okay, it's getting wider, smaller and smaller. Oh, the values okay. The values bigger than h, bigger than h, bigger than h. Oh, getting equal to h, getting equal to h, getting equal, gets lower. The point where it gets lower, the p disrupts itself. The momentum goes crazy. It increases. The uncertainty in the momentum increases. You can see the spread, the point widens. Why does that happen? That happens so that at the end, the multiple of these two is greater than h. That's why it happens. That's why the laser spreads out at the end when the slit becomes very narrow. The universe is ensuring, okay, that the value of the delta x and delta p is greater than h. Okay, this is the law of the universe. We cannot change this. Understand? I hope you guys understand. If not, If you don't understand things, guys, feel free to walk up to me and try to ask me. If I know, I'll try to explain it to you on the spot. But if I don't, then probably ask professor or something. I don't know. Okay, so that was that, and this is a take-home message. Take it home, whatever. And that's the lecture. Next part, I'm gonna cut, take some time, study the minimals, and then come back in the same video explain the minimals to you as well. Okay.
Okay, let's quickly look at the minimals for this lecture. Starting off, let's look at the questions which apply for this lecture only, and the next lecture we're going to look at the questions which apply for that lecture. First question over here, give the frequency and momentum of a photon with frequency f. The energy of a photon with frequency af is hf. Okay, this formula we have learned in chem as well. Let me just write it down really quick. The E, the energy of photon, is equal to hf, h being the Planck's constant. Okay. Now, this formula over here is confusing. This formula over here, really confusing. Okay. Let me explain what it basically is. It's saying over here, hf by c is equal to h by lambda. Okay. So looking at this formula, we can cancel out the Planck's constant. Boom, boom, gone. Let's remove these guys. Okay. And let's bring this guy here and this guy here. What formula do we get? We get our equation that is C is equal to lambda f. And we know this is the formula for speed of light. That's wavelength and the frequency. You have learned this before. So basically this is like, they're not telling us to derive this, but it's like a mini derivation, and this is how I just explained what this formula gives us, but don't be confused. Okay, so that's how we got that. Let's get rid of this. Okay, align in ascending order the following components. This, just memorize this, guys. I don't know how you're gonna do it, but do it. It's easy. Definition of visible light. My god, this is so easy. 400 to 50. Okay. This stuff, breaking radiation, is all in X-rays. X-rays will be done, no worry. X-rays. Over here, now, this is our stuff. Define interference. Interference is a superposition of waves that results in generation of new wave pattern. I define interference in a very simple way. So you have two waves. Okay. Let's draw two waves here. Let's do this really quick. Let's draw two lines here. Two slim lines. Boom, boom. Okay. Now we're gonna draw a wave with constructive interference. Okay. Just gonna draw boom, 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 boom. Okay. Now over here we can clearly see that the crest of this wave align with the crest of this wave. The trough of this wave align with the trough of this wave, and the same continues. So when these two waves overlap each other, okay, the resulting wave will have an amplitude higher when compared to both of them. So it will be huge. Okay, they basically, this and this, the distance over here, they add up to form all of that distance. They add up on each other, which results in interference. This is called constructive interference. Okay. Now, on the other hand, though, if we were to take this and just a second. Okay. Just erase this, and this. Now, if I were to draw it like that, boom, boom. Over here, you see that the crest of this wave coincide with the trough of this wave, and the trough of this wave coincides with the crest, and you get the point. So basically, when this happens, they end up diminishing their amplitudes. Okay, they don't work together, they work against each other. And what ends up happening is, if there are two things that can happen. Let's say if the amplitude being this distance, okay, of let's label these guys. This is wave 1 and this is wave 2. If the amplitudes of wave 1 equal to wave 2, then the resulting wave will be something like this. Basically nothing, because they cancel out each other. But if suppose one of them is greater than, let's say W1's amplitude is greater than W2, okay, so what will happen is W2 will be subtracted from W1, okay. Let's see, let's try to make this a little bit more okay, see this, I'll remove that, remove that. Let's reduce their amplitudes a lot. Oh no, this is going to be constructive, I'm sorry. Okay, so they're still coinciding, still the same story going on here, but of course you can see this guy's wavelength is way smaller than this guy's wavelength. So looking at comparing these two together, what will happen in destructive interferences, this guy is going to become smaller because this wavelength is going to be subtracted from this, so that much is going to get removed, and we're going to get a smaller wave when compared to them. Like this doesn't look smaller, sorry. Yeah, something like that. You get something like that. Still bigger than this, but smaller than this. This is called destructive interference. Boom, boom, boom. Let's move on. Constructive interference, destructive. I just explained this. Go with definition, learn it because it's minimal, very important. What is a requirement for maximally constructive and maximally destructive interference? If two propagating waves, okay, this, okay. I want to add a page here. Let's look at this now. Okay. Let's look at the formula first. It says over here, for a maximally constructive wave, it says maximally constructive interference. This is the formula. Delta S, which is the path difference, should be equal to L lambda, and L can be 0, 1, 2, 3, anything. Okay. Now let's explain that formula. Let's explain it. Let's take two waves again. I'm gonna take a boom, boom, that line, and boom, there. Okay, and then I am gonna draw a wave. Okay, I'm gonna draw a wave here as well. That doesn't look good. And okay, that should be good enough. Now, for a cycle, one cycle of waves is that much. One crest and one trough make one cycle. Okay, that's one cycle. Now, let's mark a point here somewhere. Let's mark a point here. Okay, over here, both of them have one cycle completed. Okay, so what we can do here, let's imagine that I shift this bottom wave. Right now, they're in maximal constructive interference because they're lined up with each other, ready to act upon each other and increase each other's amplitudes. Okay, if these two are combined, they would be constructive interference. But now, let's say I move this bottom cycle, the bottom wave, just by one cycle. Just move it one cycle to the right. Okay, let's do that. Let's do it. I take that, combine it, and I move it one cycle, just like that. What happens is when I do it for one cycle is, you can see again that they are again in maximal constructive interference. Okay, now if I were to do the same again, let's say I have the wave like that again and again. Okay, this doesn't even look like the same thing, but my point is, if I were to do it by one more wavelength to the side, so when I increase it with increments of 1, 2, 3, 4, the alignment will always favor constructive interference and it will be maximal constructive interference. Okay, now, so that's where we get the formula from. Path difference should be L lambda, lambda being the wavelength, of course. This is the wavelength, basically one cycle. Okay, so L lambda, and I hope you understand that. Now for destructive interference, we have the formula right here. Boom. Delta S is equal to L plus half lambda. So over here, let's say instead of moving, I'm gonna just okay. Now let's move this whole cycle here, 1.5. So I move it. Let's move it this side to the left. Okay, one cycle would be till there, and a half. Okay, and a half cycle would be a trough. Okay, one trough or one crest is a half cycle. Okay, so now you can see that the peaks are lined up with the valleys, and the valleys are lined up with the peaks. So this is going to result in destructive interference. So that is that formula over here. Very important. It's like how Karen's. Now whatever. Give the condition for constructive interference for an electromagnetic wave with wavelength that much. Okay, this is basically this formula again this formula, but over here part difference is expressed as C cos alpha. Okay, done. Alpha being the angular fraction. What is the definition of transverse in longitudinal waves? In a transverse wave, the displacement of oscillation particles is perpendicular to the direction of the propagation of the wave. In a longitudinal wave, the displacement is parallel to the direction of propagation. Okay, let's take some examples for both of these things. Okay, yeah, let's do that. First, for longitudinal waves, the example I just thought of, longitudinal, oh, the spelling is amazing, is sound. Okay, so what happens in sound waves is there will be particles. Okay, let me just copy this and I will paste okay, so there'll be particles of air, for example, in the air, and due to the vibrations, what happens is that these air molecules, they are compressed and they have rarefaction, compression and rarefaction. Okay, but the particles don't move from one place to another. When sound is transmitted, the particles don't go from here to here. They remain in their position, but they vibrate, and the particle next to them vibrates, and that vibrates, and that vibrates, and that's how they send the wave. Okay, so if the let's see an example. Wait, I have the images here for the biophysics. If we go to here, you can see, oh my god, here, exactly here, regions of compression and rarefaction. Okay, and let's say this sound medium is here. This is let's say this is a guy. Okay, a horrible nose job there. Okay, this is a guy. This is our odontology professor screaming at us, and he's screaming. Okay, so this is what happens in the air. The particles compress, rarefact, but they still remain in the same place. They don't move here and there. They just vibrate, and then the sound travels this way, and the wave also travels this way. Okay, it's not actually a wave like this, but it's more this compression, rarefaction, and it's mapped out as a wave. So the direction of propagation is this. Okay, and the wave is also traveling like this. So these are parallel to each other. So this is a longitudinal wave. Okay, now when we come on to transverse, that's basically our electromagnetic waves, where our waves are traveling up and down and up and down and up and down and up and down, but they are propagating here. But then their waves are traveling up, down, up, down, 90 degrees angles all around, perpendicular to the direction of propagation, right? These are called transverse waves. Okay, so yeah, just learn the definition now. I explained what that means. Just learn this definition, and that's for the minimals of today. Thank you very much, guys.